So now that we've looked at a couple of really small examples of a population, the relationship between the population and the standard deviation that we found for our basketball players, let's take a quick look at this idea of the mean and the standard deviation of the sample mean. What conclusions can we reach? Well, for the mean of the sample mean, for all samples of size n, the mean of the variable x bar, in other words, the mean of all of the possible sample means that we could take, will be exactly equal to the mean of the population mean itself. And we showed that earlier on with our group that had to be true. But what's more, there's a relationship between the standard deviation of the sample mean and the population standard deviation, and it goes like this. If we were to take the standard deviation of the variable x bar, that's the standard variation of our population, of our sample means, it will equal the standard deviation of the variable under consideration, that is its population standard deviation, divided by the square root of the sample size itself. So whatever sample size we're taking right here, we can take the sample mean, the standard deviation of the sample means, to be the standard deviation of the population divided by the square root of n. And that's an amazing important fact. And let's explain what that actually means by talking about the sampling distribution of the sample mean itself. So in this example, let's look at a histogram of the sample means of 1,000 samples of 4 IQs was superimposed on the normal curve. So if we went through and we took a sample, 1,000 samples, each of size 4, and imposed them on this mean chart, well, what would happen, of course, is that our mean of all of those IQ means is going to be 100, which is the mean of the test itself, and the standard deviation will be just like we said it would be, right? We're going to get a standard deviation that looks normal, right? Our curve will be normal. And we say that if we're talking about a sampling distribution of the sample mean for normally distributed variables, if we suppose that we have a variable of population that is normally distributed with a mean mu and a standard deviation, then for samples of size n, the variable x bar will also be normally distributed and have a mean equal to the population mean and a standard deviation equal to the standard deviation equal to the square root of n. What we're talking about right here is this. Let's talk about our normal IQs. Let's say that we took samples of size 16, right? Then on our normal curve, we should expect, like in this first curve right here, that if we have a mean of 100 and a standard deviation of 16, then if we take a sample of size 4, right, then we're going to take that 16 divided by the square root of 4, which is 2, so that's a normal curve with a standard mean of 100 and a standard deviation of 8. Oh, wait a minute, let's go back here. Sure enough, 100, here's 108, here's 92, right, 8 away. Wow, that's exactly one standard deviation away from the mean. Okay. If we increased our sample size to 16, that means that our standard deviation becomes 4, so it's even closer. And this is the effect. As we increase the sample size, as we illustrated with our basketball players, and now in this normal curve for our IQ distributions, the higher the sample size, the smaller the standard deviation. So the central limit theorem is the thing that tells us that this must be the case. For a relatively large sample size, the variable x bar, that is our samples, are approximately normally distributed with regardless of the distribution of the variable itself. And it always happens this way, right? Consider this guy. Let's say that we took a relative frequency histogram for household size, right? This is the raw data right here. We took looked at a relative frequency of the number of people in each household, and we looked at how relatively that came up, right? And we said, well, the relative frequency was 35% was the highest, right? 0 is the lowest, and for one person, 2 people, and so on, we found these frequencies. Well, if we went through and we took a mean of 1,000 samples of 30 households and superimposed them on the normal curve, look what happens. This is from actual data, folks. This is what really happens. It becomes a normal distribution. In other words, it doesn't matter what it looked like originally. If we start taking samples of size n and then just do it over and over and over again, all of the samples will fall within this normal distribution mean, which means that our normal curve is a very useful tool for helping us decide something about the nature of those means of our sample, right? And that we can use that, in fact, to tell us something about the population mean itself. So, suppose that a sampling distribution of the sample mean, this is what we need to say. Suppose that a variable x of a population has a mean mu and a standard deviation of sigma. Then for our samples of size n, for all samples of size n, the mean of the samples will equal the mean of the population, as demonstrated. Not only that, the standard deviation of x bar equals the population standard deviation, and we divide by the square. We do that by getting this sample standard deviation, or the population standard deviation, and dividing it by the square root of the sample size. So if x is normally distributed, so is x bar regardless of the sample size. And finally, if the sample size is large, x bar is approximately normally distributed regardless of whatever the original distribution looked like. Always true, right? Our distribution, if we had a flat normal kind of curve, right, certainly increasing the sample size causes this sort of normal distribution to occur. If we had a reverse J-shaped distribution, increasing the sample size that we take increases that probability to being a fairly normal curve, even for a uniform distribution, right? This is what happens. It always goes to that same normal distribution. That's really interesting, and that's really useful to us. Let's illustrate the point. When designing elevators, an obviously important consideration is the weight capacity. And an Ohio college student died when he tried to escape from a dormitory elevator that was overloaded with 24 passengers. Can you imagine getting on an elevator with 24 passengers? So the elevator was rated for a capacity of 16 passengers with a total weight of 2,500 pounds. And if you've ever been stuck on an elevator with a lot of people, you start getting really nervous, and there's a reason for that. So, let's say the weights of adults are changing over time, but the table below shows the values of some recent parameters. In the following, we're going to assume a worst-case scenario in which all of the passengers are male, which could easily happen in a dormitory scenario. And if the elevator is loaded with a capacity of 2,500 pounds, if we have 16 males, that means the mean weight, 2,500 divided by 16, would be 156.25. Well, let's look at the population. For males, the mean weight is 182.9 pounds with a standard deviation of 40.8 pounds. The distribution is normal. Similarly, for females, 165 is the mean weight. 45.6 is estimated to be the population standard deviation, and it's also normally distributed. So let's just talk about the males here now, because we want to figure out what's going to happen for getting 16 males with a mean weight not more than 156.25. All right, so let's check it out. How could we do this? Well, let's find the probability that I randomly select a single male that has a weight greater than 156.25 pounds. So let's go to Excel and calculate this, right? We have our mean of 182 and our standard deviation of 40.8. So in Excel, here's the way that we work this out. Let's go ahead and just get an empty sheet right here. Oops, that's the wrong thing I wanted to do. Let's just zoom in here just a little bit so I can see what I'm typing in. Okay, remember our command for finding a normal probability is norm.dist. Right, we're going to take norm.dist. We're going to put in our mean. So we said, well, 156.25 pounds is our mean weight that we want to find. But we know that the mean for the population is 182.9 pounds. And the standard deviation is 40.8 pounds. And so we're going to pick true, T-R-U-E. And this is the probability that we get a male that has a weight less than 156.25. Let's just make sure my numbers are right, right? We want to find what is the probability that we have a male weight greater than 156.25. Oh, wait a minute. Okay, so we can just calculate what it is to get less than that, right? This is less than a probability that A is less than 156.25 pounds. So what do we want to do? We want to get the probability that it's greater. So what we have to do, remember, is that we're going to take 1 minus the probability that A is less than to get the probability that A is greater than. All right, so let's work that out. That's going to equal 1 minus our probability right here. And, oh, there it is. 0.7432. 0.7432. So our probability of just randomly choosing a single male adult with a weight greater than 156.25 is going to be a 0.7. What did we say? I better go back and just take a quick look here. Oops. 0.7432. 0.7432. 0.74. Come on now. My pen doesn't like cooperating with me some days. 0.7432. All right, so this is our problem. So we've got a 74.32% chance of just randomly selecting a single male with a weight greater than 156.25. Pretty high chance, actually. All right, now let's go to our sample. So what is the probability that a sample of 16 randomly selected male adults has a mean weight greater than 156.25 pounds? So remember that what we're going to do is we're going to use our sample mean equal to the sample of our mean heights equal to the population sample, but we're going to get our standard deviation of our sample means equal to our 40.8 divided by the square root of n. That means that we're going to use 40.8 divided by the square root of 16. And if you work that out, that is 10.2. So now we're going to use 10.2 as our standard deviation of our sample means of size 16. All right, how does that change our calculation? Well, let's go to Excel and find out. All right, so this time now, we're going to take norm.dist, and we're going to choose a mean weight of 156.25, a mean weight for the population of 182.9 pounds, but this time a standard deviation of 40.8 divided by the square root of 16. That's 10.2 pounds, and we pick true because we want the cumulative distribution. Ooh, much smaller chance of getting something less than that. Of course, we want the probability that A is greater than, right? Is greater than. So we're going to have to take 1 minus, right? So we're going to take equals 1 minus that probability. Oh my, 0.9955. That's a pretty high probability. 0.9955. In other words, I have a 99.55% chance that if I have 16 males climbing on an elevator, that their mean weight is going to exceed 156.25 pounds, and we're going to exceed that maximum elevator capacity of 2,500 pounds. Ooh, I think I'm going to avoid that elevator. All right. So, statistically speaking, what is the maximum number of students you would be comfortable with, statistically speaking, of getting on an elevator with a capacity of 2,500 pounds? Well, there's a lot of ways to answer this one, but let's take a look at our mean, right? We have if we're talking about male students getting on and a mean weight of 182.9 pounds, what should we say? Well, let's take that 2,500 and divide it by 182. Let's just see what happens here. So let me go to my desk here. Let's take that 182. If I had 2,500 and I divide it by 182.9, what number do I get? 13.6 students. Well, still, remember, we're talking about an average rate, and even if we talked about a sample size 13 or 14, right, we're going to still get some numbers that are pretty high. I might say at most 13, if that were the way, but what do you say? What do you say? Is there another way to calculate this? I'm going to leave this one up to you, and this is a good exercise for you to think about in your responses. I'll see you in class. Have a great week, everybody.